All right, today we're diving into a mathematical mystery that stumped the greatest minds for centuries. It's an incredible story of genius, tragedy, and the discovery of a hidden, beautiful structure in a place no one thought to look. Okay, so let's jump right in. You probably remember the quadratic formula from school, right? It's this nice, clean formula that can solve any equation of the second degree. But what happens when you get to the fifth degree, the quintics? Well, for hundreds of years, mathematicians were on the hunt for a similar formula, and they came up completely empty. The real question wasn't just what the formula was, but why couldn't anyone find it? You know, the solution to this puzzle turned out to be one of the most profound ideas in all of math. It wasn't about being more clever with algebra. It was about seeing something deeper, something no one had seen before. A hidden symmetry baked into the very structure of the equations themselves. To really get why this was such a breakthrough, we first have to understand the roadblock. For a really long time, it felt like progress was moving along just fine. So way back in the 16th century, mathematicians totally cracked the code for third and fourth degree equations. It seemed like they were on a roll. Then, a couple hundred years later, a guy named Joseph Louis Lagrange has this key insight. He starts looking at what happens when you just swap the answers, the roots of these equations. But then everything just stopped. In 1824, Niels Henrik Abel proves, definitively, that the hunt was pointless. The formula just doesn't exist. And that changed the whole game. The question wasn't, where's the formula anymore? It was, why is there no formula? And the person who finally gave the world that explanation wasn't some esteemed professor. Oh no. He was a young, brilliant, hot-headed French revolutionary. Evariste Galois. The guy was a true prodigy. By the time he was 18, he had developed a theory so new, so completely out there, that when he sent it to the French Academy of Sciences, they basically threw it in the trash. They just didn't get it. His life was short, it was turbulent, and at just 20 years old, he was killed in a duel. Knowing he was probably going to die, he stayed up all night just frantically scribbling down his mathematical legacy in a letter to his friend. It's just an incredible story. And that work, those frantic notes from his last night on Earth, just sat there, in obscurity. It took 14 years for another mathematician, Joseph Liouville, to finally stumble upon them, realize the staggering genius in those pages, and share it with the world. 14 years. So what was it? What was this revolutionary idea that was so hard for people to wrap their heads around? Well, it all came down to looking at the answers to an equation in a totally new way. Okay, first, a real quick refresher so we're all on the same page. The roots of an equation are just the solutions, the numbers you plug in for x that make the whole thing work out to 0. They're the answers we're trying to find. All right, let's take a simple one. X squared minus 4x plus 1 equals 0. It has two roots. We'll call them a and b. One is 2 plus the square root of 3, and the other is 2 minus the square root of 3. Now, they're obviously different numbers, but you can see they're related, right? They're a pair. Now, this is where the magic begins. This is the start of Galois' big idea. Check this out. If you add these two roots together, you get a nice simple number, 4. But here's the key move. What happens if we swap a and b? Well, b plus a is still 4. The relationship holds true. This might seem super obvious, but it's actually incredibly profound. It turns out that any relationship you can write between these roots using regular rational numbers will still be true even after you swap them. This unbreakable property, that's the symmetry Galois discovered. So here's the big leap. Galois realized you could actually create a whole mathematical structure, what we call a group, out of these swaps. This Galois group is like the equation's unique fingerprint. It captures every single way you can shuffle the roots around without breaking any of their essential relationships. It is the deep symmetry profile of the equation. And this abstract idea, this symmetry group, held the key to finally solving that centuries-old mystery. This is it. This is the core of the whole theory. Galois proved that an equation has a formula, one using things like square roots, cube roots, if and only if its Galois group has a very special kind of structure. Think of it like a tower that can be broken down piece by piece in a very specific, predictable way. Modern mathematicians call these special groups solvable groups. And this table just lays it all out so perfectly. For equations of degree 2, 3, and 4, their Galois groups, they have that special solvable structure. They can be broken down in just the right way. But then you get to degree 5, and its symmetry group called S5, it's just different. It does not have that structure. It is not solvable. And that's the answer. That's why there's no general formula for the quintic. Its underlying symmetries are just too complex. The structure of its Galois group simply won't allow for that step-by-step breakdown that a formula needs. Galois didn't just say it was impossible. He showed us exactly why it was impossible on a fundamental level. But the story doesn't stop there. I mean, Galois' idea was so incredibly powerful that it reached far, far beyond the one problem he was trying to solve. His theory built this amazing bridge between two worlds of math that had always seemed totally separate: the study of numbers and fields on one side, and the abstract study of symmetry and groups on the other. This connection is now like a cornerstone of modern algebra. And get this is one of my favorite parts. The exact same tools Galois developed were used to finally solve problems that had baffled the ancient Greeks for 2,000 years. Using his theory, mathematicians could finally prove once and for all why it's impossible to do things like trisect any old angle or double the volume of a cube using just a compass and a straight edge. It all comes back to the symmetry of the numbers involved. And while other people, like Abel and Ruffini, had already shown that the quintic was unsolvable, Galois gave us the complete picture. As one mathematician, Alan Clark, put it, his way of explaining why dramatically supersedes their work. He gave us the universal framework. So it kind of makes you think, doesn't it? The next time you run into a problem that just seems impossible, maybe the question to ask is the one Galois answered. What are the hidden symmetries at play here? Because understanding that deep underlying structure might just be the key that unlocks the whole thing.